Hi, this is Mark Weitzman. Welcome back to Quantum Field Theory, a student's perspective. At this point in time, I want to continue with lesson, lesson 3, Canonical Quantization of Scalar Fields. This is part 2. And so part 2 is constructing a scalar quantum field. So we continue with Sidney Colemans program. Which is, as I mentioned earlier, basically a bottom-up approach. And we're going to construct a quantum field theory. And we seek fields which will be Lorentz covariant. For a scalar field, I guess we could say invariant, but those terms are sort of used interchangeably. We wanted to obey locality. And we wanted it as simple as possible. Now, as I've said, this lecture is sort of an optional lecture in the sense that in the next lecture, lecture 3, we'll use the standard canonical quantization approach, which is like a top-down mechanical approach. And so right now we're sort of using a more physical approach that Coleman starts with. But not all books proceed this way, and it's always hard to see which came first. This is sort of like a chicken and egg idea. So Coleman has 5 conditions. For a scalar field. Okay. The first one is the locality that we talked about earlier. So observables, this basically means observables outside the light cone commute. Okay. The second, and we've discussed that earlier in the class about why we need this to happen. The second condition is we want the field to be Hermitian. And thus observable. Now we will later on talk about charged scalar fields, which are non-Hermitian, We can combine fields. We could take two real scalar fields and then combine them in a way that they're not an observable or they're not Hermitian, but we wouldn't consider that just to be one scalar field. So for now, this is the simplest possibility we want to start with, is a single field, but we can combine them, and we'll see that later. Third condition. So this is just a usual condition for translation properties under the Poincare group. And we've discussed those before. Fourth condition. It's very similar, only now we're talking about Lorentz transformations. So this is just saying that fields transform as scalars under a Lorentz transformation. If we were dealing with vector fields or tensor fields, there would be a matrix here. If there was some kind of matrix here, for like spinors, vectors, or tensors. But when we just have basically the identity matrix, then we're dealing with a scalar field. Okay. Now our fifth and final condition and I'm warning you right away, many times I'm going to forget the vector signs on the momentum things. I'll try and keep it in here right away, but so this is an assumption. Remember, these are conditions that we hope to satisfy. We may not be able to satisfy them, but it turns out we will. But these are assumptions that we want our scalar fields to obey. So this assumes that the fields phi are linear functions of the A's and A daggers. So if you remember at the end of last lecture, I mentioned that we're working in Fock space, and we have these A and A dagger operators lying around, and we have the states, the multi-particle states. So the simplest assumption would be to assume that phi is built from these operators. These are the only ones we know of right now, and we start with a linear idea. I mean, it may be more complicated expressions, but this will turn out to work. So this is when I said before we want the simplest possibility, this is sort of what we mean. Now, condition 3, in case you want to look it up, this is equation 2.23, 2.24 of Sugneki's book. And remember that there's a difference in the metric that Coleman is using and that Sugneki is using. And condition 4 is equation 2.26. And so just in case you want to look that up. Now, in the last lecture, we'll need it this lecture, but I forgot to work out the Lorentz transformation properties of the A and A dagger operators. So let's work them out right now. We know that we have a unique vacuum state. So even if we make a Lorentz transformation, the vacuum state doesn't change. I'm sorry. Should be this. And for a single particle states, we've always assumed, it's hard to remember what we postulated and what we didn't, but I'm sorry again. So this just says under a unitary Lorentz transformation, we're going to map a state P, and the Lorentz transformation is lambda to the state lambda P. And for multi-particle, we assume an obvious thing. Now we would have U of lambda acting on a state which has like many particles with various momenta. And this would just be, lambda would act on P1 and lambda would act on P2 and lambda Pn. So nothing unusual going on here. Now, let's see how I'm going to switch back and forth in this lecture between the A and the alphas, the A daggers and the alpha daggers. These are the relativistic, and they have different normalization and different commutation relations. Basically, they're just proportional to each other, so switching back and forth doesn't harm any arguments and everything. So let me just start to show you how to derive the Lorentz transformation property of the operators. By definition, we have this from above, and now this is equal to because that's what the A's or the alpha daggers do. An alpha dagger P creates a state with momentum P out of the vacuum. And then we can write this as because all I've done is I've inserted this, which is equal to 1, because we have a unitary transformation. Okay, so this is equal to, by the way, this part over here on the left-hand side, this is just, I left out an equal sign here. This is equal to, this is just alpha dagger lambda p acting on the vacuum. Again, we create a state with momentum, a particle, single particle state with momentum, the transformed p, lambda p. So this is equal to u of lambda alpha dagger p u dagger lambda acting on the vacuum. Because, as I said earlier, there's only one vacuum, so u lambda acting on the vacuum is the vacuum. Okay. So this implies that alpha dagger lambda p is equal to u lambda alpha dagger p u dagger lambda. Again, we're physicists here, so you know, the fact that we've proven this for the vacuum state, one might say, how do you know it works for all states? But you can easily see that it follows. You can give a more rigorous argument if you're in a math class. And taking the Hermitian conjugate of this, we would get alpha, or just doing the same argument over again. So I'm going to box this over here. So this is how our alphas and a's also transform under Lorentz transformations. And we can use the same kind of logic. I'm not going to waste time on doing it. Likewise for translations. We get e to the I p dot x alpha dagger p. The large p's are operators, momentum operators. I just don't know why. Now I can software, which is equal to e to the I, and the small p's are actually just momentum vectors. And in the same way, I'm going to box these as well. Okay. Schrodnicki has problems in his book at the end of chapter 3, 3.3 and 3.4, where he derives these transformation properties, but he's proceeding in a different order. Because he has the fields in terms of the operators, and he knows how the fields transform, so then he gets how the A's transform. But we don't have the fields yet, so we're proceeding in a different order. That's all. Okay. So now I want to start to use our conditions and to find the form of the field. And what we'll do is we'll proceed backwards, actually. So using 5, and again, going back and forth between alphas and a's doesn't really make a difference at all. We can write phi of 0. Let's go back to condition 5. We'll use this thing, but now we're going to use a relativistic measure, so we're going to change these to scalar relativistic things and use the alphas instead. And again, this is the same. Now we're going to rename what we had before when we used the alphas. And remember, P is a 4 vector. And P0 is always defined by omega P, square root of P squared plus M squared. Okay, so all we did was substitute in 0 for that general expression we had. And our goal is simply to determine the F's and the G's and the most, put whatever constraint we have. Okay, so now we're going to use condition 4. A special case. I'm going to have u lambda phi 0 u dagger lambda is equal to phi 0. And this is because lambda inverse 0 is equal to 0. And that's the same thing as lambda 0 equals 0. So let me scroll back to condition 4. And I'm just substituting x equals 0. So lambda inverse of 0 is 0. So I get what I wrote down. It's all very simple substitutions. The argument is really quite simple. Okay. So now, since I have, I'll substitute this expression into here. So now I'm going to get phi 0, that's this, is equal to u lambda Okay. Now, these are operators. The u's are operators. Everything else is numbers except for the alphas, which are also operators. So we can move everything inside. So this is equal to the integral d3p with the relativistic measure. Then I'm going to have f of p u lambda alpha p u. Took me several years to learn how to write lambda without an a. It's just something in my brain. F of p u lambda alpha p U lambda dagger. Something in my brain that just always writes that as an A. Plus, you'll have to excuse me. U lambda alpha dagger P, U dagger lambda. Now, this part over here, why does it do that? This part over here, we showed earlier that the way that alphas transform, this is just U lambda P. And this part over here is just alpha dagger lambda P. Okay, so that's good. So we have, we'll just write it down again. We've established that phi 0 is equal to the integral d3p 2 pi cubed 2 omega p f of p alpha lambda p plus g of p alpha dagger lambda p. Now, if we remember that this whole measure over here is Lorentz invariant, and we make the substitution p prime equal to lambda p, the measure remains unchanged. It's just d3p prime over 2 omega p prime. This changes. This becomes p is equal to lambda inverse p prime. So, f of p will go to f of lambda inverse p prime. G of p will be equal to g of lambda inverse p prime. And then I'm just going to relabel everything p. So we're going to end up that this whole thing phi of 0 is the integral d3p 2 pi cubed 2 omega p f lambda inverse p alpha p plus g lambda inverse p alpha dagger p. Now if we compare this final expression with what we started with back here, the only changes that, remember the alpha p's are like, and alpha dagger p's are independent operators for each p. So the only way these two expressions can be equal is, so this implies that f of p is equal to f lambda inverse p, and g of p is equal to g of lambda inverse p for any p and any momentum and Lorentz transformation. So basically, okay, we have shown that f of p is a constant, and g of p is a constant. Because we can start on any reference frame, we can start, and then if we go to another reference frame, it doesn't change. So once we determine it in one reference frame, it's going to be the same in every other reference frame under a proper Lorentz transformation. So, in other words, lambda maps p to like p prime on the mass shell. So f and g are constant on the mass shell. And if we go back to that condition that I said earlier, you know, P is a 4-Becker, but it's constrained. It's always on the mass shell. And the positive mass shell. Okay. So we are down to 2 constants for phi of 0. Now, using our translation idea, which we said earlier in one of the conditions, this is condition 3. And we get this equation, we will relabel variables, x to 0. So let me just scroll back to condition 3. If I set y to minus x, I have e to the I p dot x, phi 0, e to the minus I, p dot x. I think I left off something when I said that. Yeah. Okay, I left out that this is phi. You know what? Let me, because I want to be consistent with that. This is equal to phi of x minus y. And so when I set x to 0 and y to minus x, I get phi of x over there. So that's where this equation comes from, in condition 3. And then, once again, do the substitutions of the field for the phi of 0. And I get phi of x is equal to e to the I p dot x and then once again bringing the operators inside, and then using the transformation properties that I established, the ones that I said I forgot, you'll see that this easily works out to be so. The only thing I learned here is that we still have 2 constants, except now I've established this for the field at every space-time point. So now I have an expression for the field everywhere. It comes down to 2 constants, f and g. Okay. So we've used conditions 3 to 5, and we've established this. Now I just want to rewrite this as just to show you how it's usually written. We'll write this as f phi plus x plus g phi minus okay. You might think the order of this is backward, that this is like a e to the minus I p dot x, and we have a phi plus here, but this is the standard association in quantum field theory. Remember, our metric is positive, so p dot x is going to be et minus, so the time development time development of this term is equal to e to the minus I et, which is the standard positive time development in QM. And this will have the negative time development. So there's some logic to this, even though it's opposite the exponents. And then if you go to a book like Czarnecki, he's going to have the opposite signs in the exponents, so it can get confusing. Anyway, so here on these definitions, and just from here you can see that phi plus x, d3p. I'm just going to put the a's back in here. I'm putting the a's in. You might say, why am I going back and forth? Turns out that the a's and a daggers are more convenient when we use the commutation relations, which we're going to get to in a second. I'll box these. Okay. So condition 2 says phi is Hermitian. And you can see that when we take the Hermitian conjugate of phi plus x, it becomes phi minus, and this becomes phi plus x. And it turns out that basically we're going to get f equal g. Actually, there is some phase conditions, but we can get rid of various phases by redefining the A and A dagger operators. We put the phases in there. So I'm just going to get that our Hermitian field, we're now trying phi of x is equal to phi plus x. Obviously, there's a normalization constant on whatever f is, but we don't have to worry about that now. Plus phi minus x. So now we have to check. Condition 1 to see if it's satisfied. So we have phi x, commutator of phi x and phi y is equal to the commutator of phi plus x plus phi minus x, comma, phi plus y plus phi minus y. Now this is equal to commutator of phi plus x, phi minus y plus the commutator phi minus x, comma, phi plus y. So why are there no cross terms? Why don't we have to worry about phi plus x and phi plus y? Well, just go back to the definitions. Phi plus x and phi plus y both involve the A operators, and the A's commute with each other. And similarly, phi minus x and phi minus y involve the A dagger operators, and they commute. So it's only a plus with a minus or a minus with a plus that we have to worry about. Okay. And it's obvious if I rewrite this that they're sort of the same. I only have to do one calculation because I can put a negative sign to put this second and switch variables x and y. So now we have phi plus x phi minus y commutator is equal to the commutator, and just substitute in our definition of the fields. Commutator of that. When we do the other field, we have to use a different variable for the integral. So I'll use p prime. Okay. Now this is just taking again, commutators only apply to operators, so we can take all the integrals and scalars and numbers out. Just want to correct something in my notes. Okay, and we know that this over here is just equal to del 3 p minus p prime. So that lets us do one of the integrals easily. So this turns out to be equal to the integral d3p 2 pi cubed 2 omega p e to the minus ip x minus y. This is defined as del plus x minus y. Every book uses different conventions between what they call del plus, del minus, del 1, del 2, so don't worry about it. What's important is this is a Lorentz invariant function. We have a dot product between four vectors in the exponent, and we have a relativistic measure. So this is Lorentz invariant. I'll just write that down, that del plus x is equal to del plus lambda x. So del plus is Lorentz invariant. Now, using what I said before about just interchanging the fields and switching the labels, it's easy to see that minus del plus y minus x. Just use the definition of the del functions. Okay, so substituting these two things in there, we get the commutator of phi x with phi y is equal to del plus x minus y minus del plus y minus x. And now this is defined as I del x minus y. This will be important. This is sort of the Feynman propagator for scalar fields. And again, what we need to show we need to show if we're space-like. Now we don't even really have to do any calculation for this because this is a 4 vector. But if it's a space-like 4 vector, let me draw. It's going to be hard for me to draw. This is the standard special relativity diagram. This is the mass shell. And these are the other shells for things which are space-like. So if we have a vector, let's say here, let's say this is x minus y, this vector here, we can make a Lorentz transformation to get it to its negative here. This is minus, if this is x minus y, then this is minus x minus y. Now you might say, how do we know this? Well, I should have drawn the light cones here. How do we know that we can do that? If you think of what this is, we can just rotate it. This is a sheet, but it's not disconnected from this. Remember, there's an extra dimension which I can't show here. But this whole thing can be rotated around. Let's call this the z-axis. I'm sorry, not the z-axis. This is the time axis. We can rotate this whole thing around that shell. So we can get from here to here. As I said, this whole sheet is a tube. It's all connected. We can do a Lorentz transformation from here to here. Then we can go on here, and we can do that. We're always space-like, and we can't go from this sheet to this sheet because that involves changing. From here to here would be impossible. These two sheets are really disconnected. That would involve changing the sign of time, and we're doing proper Lorentz transformations. So because we can go from x minus y to minus x minus y, this thing now becomes over here. We get I del x minus y is equal to del plus x minus y minus del plus. Remember, I said these functions are Lorentz invariant. I can certainly map y minus x to x minus y if I'm space-like. I can't do it if I'm time-like, but if I'm space-like, I can do it. And now I can make this x minus y, and that's equal to 0. Again, only if x minus y squared is less than 0. I encourage you to look at diagrams. They have these diagrams in Coleman's book and in Peskin and Schroeder, and you should really have the orientation that the sheet, the space-like sheet, is like all connected, so I can rotate around, whereas the time-like sheets on top and bottom are separated. Okay, that's a topological difference. So our result, we've established the quantum scalar field. And phi of x is equal to, I'll write them both ways. You'll see them either way in several books. This is with non-relativistic annihilation and creation operators. This is equal to and this is with relativistic and a relativistic measure. Coleman is the only book that I know that actually uses different symbols. Most books stick to one or the other and they use the same symbol. I think Suneki does that. He uses, I believe, this convention, but he doesn't call it alpha P, he calls it A of P. Okay, so with that, we're at the end of this lesson. And, if you got lost in here or somehow, no problems. Next lesson, we'll do the standard canonical quantization. We'll turn the crank and we'll get the exact same answer. So I'll see you in the next lecture. Bye-bye.